We're going to look at physics and the quantum mechanical model now as section 5.3. And really the quantum mechanical model grew out of the study of light. And it's through the behavior of electrons that we can see different spectra that different atoms will emit, and they'll become more clear as we go on. First, let's look at just a brief overview of the electromagnetic spectrum, which I always think is pretty interesting. So the electromagnetic spectrum are all the different types of waves that we know of in our universe, and we get this from the sun. So we have all these different waves: radio waves, microwaves, infrared waves, invisible waves, ultraviolet, X-ray, and gamma rays all around us. Now, to understand it, I think this is a pretty good diagram here. We need to know what wavelength and frequency is. So we'll come back to this diagram in a second. So first of all, wavelength. Wavelength is just the length between the waves. So this one has a short wavelength. This one has a longer wavelength. So the length of the wave is the wavelength. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 waves. 1, 2, 3, 4, 5, 6 waves. So in the same amount of time, we have twice as many shorter wavelengths, shorter waves going through. Now, wavelength is inversely proportional to frequency. Frequency is how often something occurs. So here we have a wavelength here, but in the same amount of time, we'll have two wavelengths here. Wavelength is how big the wave is from trough to crest. Frequency is how often it occurs. Like, does it occur boom, 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 like that, or boom, boom, boom? So if we could say that at each crest we had a sound, boom, boom, that wouldn't have as much frequency. This would have at each crest much more sound. Okay, so the frequency means it occurs more, and that's, if something's more frequent, it occurs more. So the bigger the wavelength, it's inversely proportional. That means it's opposite. So the wavelength, now wavelength is the symbol for wavelength is lambda. Symbol for frequency is nu. So we have wavelength is inversely proportionate to frequency. We have small wavelengths, means high frequency, and a large wavelength means small frequency. And here's a formula. We're not really going to do anything with it, but we can just see how we can calculate the wavelength and the frequency. So again, lambda is the wavelength, nu is the frequency, how often something occurs. So notice the units. In this case, it's meters for the wavelength, and for frequency, it's 1 over time. And c is the speed of light, which is close to 3 times 10 to the 8 meters per second. So the speed of light equals wavelength times frequency. So back to the electromagnetic spectrum. This is a spectrum of all the waves that we know. And I think it's a pretty decent chart. So we have gamma rays up here. And what can we say about the frequency of gamma rays versus the frequency of radio waves? So the frequency of gamma rays are extremely high, but the wavelength is much, much smaller. We can even just look at this pictorial representation of the frequency. This will occur boom, 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 boom very quick. The radio waves, big, long, sloping waves. And we get a picture of the wavelength in meters. So 10 to the minus 13 meters. That's an extremely small wavelength. So 1 meter is about the length of a microwave. Radio waves, those are the radio waves that you get from your tower. Let's say you're 95.5 Mojo in the morning, or 102.7 or 79 FM. All those are beaming these huge waves of radio out there. So 200 meters long, or excuse me, 100 meters long, that's the size of a football field, even bigger than a football field. They're going right through us. It's not as though they're going through us all the time, but or around us. It's not as though we can just stick our ear out the window and hear a radio wave go by. We need a transmitter for that. So we have these towers emitting radio waves to our radio, and that's how we can hear it. But they're going through us. But they have very small, very low frequency. Gamma rays, on the other hand, way on this extreme, are very, very small. Look how small those are. But that means the frequency is extremely high. Now, gamma radiation, you've probably heard about that. Thankfully, our atmosphere blocks that out. But if you remember from the Incredible Hulk, David Banner got some gamma radiation and became the Hulk. But gamma radiation, gamma rays, extremely high frequency, that means it's really dangerous. It's like, would you rather have someone just kind of hit you once with a big pillow, or many, many, many times over with a bullet? Now, X-rays down here also, are dangerous for you. They have high frequency. Bigger waves than gamma rays, but they're also very dangerous. That's why when you go to the dentist, you put on that lead shield, and the technician will stand way behind the machine. So you don't want to have too much exposure to X-rays, because with their high frequency and small wavelength, those are also dangerous. Ultraviolet, UV radiation. You know what that's from? That's from the sun, and when we're out there at the beach and we are trying to protect ourselves, we put sunscreen on to block UV radiation. So either you just cover yourself in sunscreen, or you just put a big blanket over yourself to block that UV radiation. Now over here is the visible light. And if we go way down here, and also this is something that is pretty cool. You can, as a scale, this is a scale of how big these wavelengths are. Football field, how big a radio wave is. Humans are as big as those microwaves. All right, so these are approximate size. Now visible, there's a very small range of light that we can see. The visible is what we can see. We can't see all these other waves, but we can only see the visible. And it's an extremely small portion of all the waves out there that we can see. And it ranges from, if you can see down here, violet all the way to red. And it makes sense too. We have violet here and red. So remember our visible light spectrum, Roy G. Biv. Violet, ultraviolet, all the way to red, infrared. We'll talk about visible light in a second. So infrared rays are larger wavelengths, and they're not as dangerous at all to us. Then we have microwaves and radio waves, much bigger wavelengths. The visible light that we're going to look at here as far as chemistry. So how does visible light go with chemistry? When atoms absorb energy, electrons will move to higher energy levels. So remember our energy levels that we were just talking about. We have an electron, they will move to a higher energy level, and when those electrons lose energy, they will emit light when they come back down to their ground state, when they return to a lower energy level. So that is the atomic spectrum. So we get energy, our atom gets energy, the electrons will go to a higher energy level. When they lose the energy, they will emit light. Now this is how fireworks work. Fireworks work this way because each atom, each element will have a characteristic color that it produces once it absorbs a certain amount of energy and then returns to its ground state. Ground state, that's when an electron is the lowest possible energy. That's their ground state. And it will take energy to move them to a higher state. Now, when that electron moves from a higher to lower energy, it originally needs to get energy here. So it gets energized. It will go to a higher energy level. Then it will come back down. And when it comes back down, it will emit a light. Now that light emitted by the electron moving from the higher to the lower energy level has the frequency directly proportional to the energy change of an electron. The electron will get energy and emit it. This energy, so the color will correspond to the amount of energy. So the higher frequency has higher energy. The higher frequency of color will have the higher energy. The lower frequency of color will have lower energy. Which ones have the higher energy? The higher energy here, higher energy. This is lower energy. Higher frequencies, higher energy. So which color here has the highest energy? That would be purple, closest to the higher energy, higher frequency. The red has a lower energy. So the red, lower energy, violet, higher energy. And we can see here the blue has higher frequency, smaller wavelengths, means higher energy. This one has higher or larger wavelength and lower frequency. And then green is in the middle. So remember, Roy G. Biv, this is a lower frequency by infrared. This is a higher frequency by ultraviolet. In a firework, a certain amount of energy is given that will cause an electron to go up, and this is just an example. And once it leaves, depending on what type of element that is, it will emit a certain color. Now, each element has their own specific atomic spectra. So given amount of energy, certain element, maybe lithium, will cause, once it has energy, is energized and goes back to its ground state, it will cause a certain color to be emitted. So people who are making fireworks use different sorts of elements. People who are using fireworks, those professional fireworks, people don't just randomly think, oh, okay, let's color our fireworks with some paint. Each different firework color has a specific color to it because of the atomic spectrum. And when that element is heated, when that usually is salt, that element is heated, extreme energy, the electrons will go to a different energy level, and then when it comes back down to its ground energy level, a color will be emitted. So if someone knows a certain color that they want, say a red, they'll use a certain element. If they want a yellow, they'll use another element. If they want blue, they use another element, because each will emit, when they come back down to their ground state, a certain type of color. Now we'll see an example of this when we do flame tests. Now a flame test, we will have certain salts which have certain elements, and we heat it, and then we'll see certain colors. And those colors will correspond to different elements. And we will see that with the flame test.